Now, let's talk about the idea of the gradient vector. It's really a very kind of special vector that we have a lot of applications for. Now, this directional vector in the direction of u, and just as a reminder, u is in fact a vector, can be written as the dot product two vectors. I could very easily simply write this, or just as a reminder, equals partial of x times, well, a. Let's just use a. And plus the partial with respect to y. Of course, let's use b. And I can write that as simply the dot product of the partials with vector u, which is at ab. So, of course, rewrite that again. It's a partial of x, partial of y, dot u, where u is that unit vector in the direction that we want to go. Now, this guy right here is used for a lot of applications, not just in the directional derivative. Because of this, we give it that special name, and it is called the gradient of f. And it has the special notation. It's the upside down delta of f, or is sometimes written out as grad f. Now, this delta, this upside down delta, this guy is read as del. And very commonly, we simply refer to this as simply del f. So this gradient vector is defined as follows. If f is a function of two variables, obviously x and y, then the gradient of f is the vector function del f defined by the gradient of f, of course, of xy, equals the partial with respect, the vector consisting of the partial with respect to x and the partial with respect to y, which we could write as the partial of f with respect to x I plus the partial of f with respect to y j. Now, with this notation, we can represent the directional derivative. This guy back up here. We can represent the directional derivative as directional derivative of f. And I'm dropping this notation, this of xy. I think we kind of know that that's there. This is actually equal to del f dot u. So I can write this entire directional derivative with this simple notation, because this really is nothing more than this same dot product that I wrote right there. Now, this expresses the directional derivative in the direction of u as a scalar projection of the gradient vector actually onto u. Now, think about this for a second. Recall the interpretation and the application, the way we used dot products when they were first introduced. If I had some vector, say a and b, we thought of the dot product of a dot b as the scalar projection onto b, how a is projected onto b. And that's exactly what this gradient is. It's the how the gradient vector is projected onto this unit vector.